Hello, y'all, and welcome to Lesson 30, Structure 3.1.3, Part 2. So we're going to continue where we left off on periodicity. Specifically, now we're going to be looking at ionization energy, electron affinity, and electronegativity. However, this is all heavily based on atomic radius. So if you did not look at Lesson 29, the previous video, I suggest you go back and do so because we're going to reference it a lot. So when we look at these trends, we're going to start off with ionization energy, which we talked about back in structure one. We'll abbreviate ionization energy to IE. Now, this is usually when we talk about this, we're talking about removing the outermost electron. In other words, the valence electron from an atom. However, there's a very specific definition that I've seen on the IB exam as a question. So the actual definition is the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms. Usually, this is in the units kilojoules mole inverse, usually. So that's the actual official definition for ionization energy that you may be required to answer on an IB exam. I've seen it before, and they often reuse sections of questions in different forms. But what does ionization energy actually look like in an equation? Well, generally you are required to know that too. So if we take sodium, Na, and we ionize it, in other words, we remove the first electron, that would be first ionization energy, we would get a sodium ion positive. We must remember that these are gaseous, and we're left with 1 electron. So this is what the equation for ionization energy looks like. You should be able to do that with almost any element. Now, how does ionization energy change over time or change with elements? So what we can do is we can look at a graph of the first ionization energies, and I'm actually going to import another graph that we used the other day, atomic radius. So let's look at these two graphs side by side. You'll notice that we have this repeating trend. We go up, then we go up, then we go up, and you can assume it goes up. This is period 1, this is period 2, this is period 3, period 4, or if you're more comfortable, we can talk about energy levels. This is n equals 1, n equals 2, n equals 3, n equals 4. You'll notice a similar pattern with the exception of the first energy level, n equals 1, n equals 2, n equals 3, n equals 4. These patterns are periodic. We have periodic patterns, probably where the name for the table comes from. And you'll notice that as radius goes down, decreases, ionization energy increases. Now, we can figure out why that is. Ionization energy is based off the attraction of the valence electron with the nucleus. And generally a stronger attraction, we have a higher ionization energy, meaning it requires more energy to separate two things that are stronger together. Now, why might that be? This is where all these trends are going to come down to. It comes down to electrostatic interactions, which are based on two things, the charge magnitude. In our case, that's going to be the effective nuclear charge, and the distance. In our case, that's going to be the radius. So if we want high interactions, we need two things. This needs to be large, and this needs to be small. Therefore, elements that have a very small distance but very high effective nuclear charge will have high ionization energy, and we see that. If we look at neon, neon here and neon here, it's a small element, so the radius is small, but its effective nuclear charge, if we were to do the math for neon, it would be 10 minus 2, which is 8. That's very large for an effective nuclear charge. That's about the largest it can be without going into ions. So due to this equation, we can see that neon is going to have a high ionization energy, and we see that right here. It's very hard to remove the electrons off neon. So if we were to make a graph of our periodic table and set our trends for our periodic table like we did with the radius, we tend to see an increase in ionization energy. So as the atoms get smaller and as the atoms get more, have a higher effective nuclear charge, it's harder to remove electrons. So that is ionization energy. Moving on to electron affinity, which I will also abbreviate as EA. Now, electron affinity is kind of like the opposite of ionization energy. This is the energy released when an electron is added to a neutral atom. And similarly to ionization energy, while they're not going to make you define it on the IB exam, I've never seen it, we generally refer to it when we're talking about 1 mole of gaseous atoms and 1 mole of electrons added. And we also usually talk about it in kilojoules mole inverse. That's what it is in your data booklet. By the way, all the values for these, for electron affinity, ionization energy, and electronegativity, as we'll go over later, are in the data booklet section 789, somewhere around there. All right, so we also have an equation for adding electrons. Generally, a good example might be like hydrogen gas plus an electron will create hydrogen gas with a -1 charge. And again, we're looking at the attraction of electrons. Well, what governs the attraction of electrons? Much like ionization energy, the attraction is from something maybe not the valence electron, but it will become a valence electron attracted to a nucleus. And if it's smaller, so if there's a smaller radius, it's going to have that higher interaction. So it's kind of like the action is the inverse of ionization energy, but the result is still the same. Small atoms with high electron affinity or high effective nuclear charge will have a stronger electron affinity. So generally want to change colors. The magnitude of electron affinity increases with stronger electrostatic interactions. And what I mean by that is we want small radii and large effective nuclear charges. There's a couple exceptions with electron affinity, however, so we're going to kind of make those exceptions right here. So generally, noble gases, which are going to be part of this other thing, and atoms with full sublevels. So an example might be magnesium, which has 1s, or sorry, its full sublevel is, whoops, not 1s, it's 3s2. So it has a full 3s2 sublevel. Do not tend to accept electrons. Therefore, no electron affinity. So they tend not to have an electron affinity, mostly because they won't accept the electrons anyways. So similarly, we can make the trend for electron affinity, though, that it also increases. So electron affinity and ionization energy have inverse trends to radius because a smaller radius means a larger other value. The last one is electronegativity, which I will also abbreviate EN. And electronegativity is the only one where we're not talking about a mole of something, but this is just generally the tendency to accept a shared pair of electrons in a covalent bond. Now, we haven't discussed covalent bonds yet, but you probably already have a little bit of background on them. So when two atoms are bonded and they're sharing electrons, the one that will pull on that more. Um, oops. And instead of accept, that's not the right word. I should use attract. They're all going to accept electrons in a shared bond, but the tendency to attract those electrons. Now, this is also based on, you guessed it, electrostatic interactions. If we look at maybe not helium, a hydrogen atom with its one electron, and maybe a fluorine atom with its many electrons, its nine, but seven valence electrons, and we bring these two together. I'm going to move this electron here. Oops, not the tool I wanted. Then we bring these two together so that they overlap a little and they share that electron. Something you may realize is that hydrogen can pull on it with an effective nuclear charge of +1, while fluorine can pull on it with an effective nuclear charge of +7. So if we look at our Z effectives. So we have a little bit of attraction here and a lot of attraction here. Now, again, they're pulling on all those electrons. So what generally tends to happen is that the electrons shift towards fluorine. And we can see that because fluorine can pull so much harder, it would therefore be more electronegative. It is attracting those electrons stronger. So it has a similar trend to our ionization energy and electron affinity for very much the same reason. We will increase electronegativity across a group or across a period and decrease down a group. So these all have similar trends for that same reason. As the atoms get smaller and the effective nuclear charge gets bigger, these values increase. We also have these exceptions with electronegativity in that noble gases do not form covalent bonds or bonds of any kind, and therefore have no electronegativity values. So to recap this whole thing, the best thing to do is look at a big periodic table chart. So here's our general table, and we just draw a big arrow across it, going from bottom to top, and you're going to have to remember your exceptions. Atomic radius will decrease. However, ionization energy, electron affinity, and electronegativity will increase. And this is a general trend. These trends don't necessarily need to be memorized because once again, all the values are in your data booklet, which you get the whole time. But this will help us explore and explain other values and other ideas down the road without you having to pull up every individual value. It's very good to just have these trends memorized and set, and they will help you so much down the road. With that, I hope this all helps and have a great day.